Okay, so here we are back at the second part of simple harmonic motion. And this is where we finished, at least for EMOD, doing the sinusoidal nature of simple harmonic motion, and we covered velocity. So let's continue thinking about that and look at the mathematics. This top curve is a graph of A cosine omega t. The bottom curve is the same, but phase shifted a quarter period so that it's a sine function rather than a cosine function. So really, all cosine and sine waves have the same shape, and we call them sinusoidal. So if you shift this back a quarter period or forward a quarter period, you get a sine wave, but a sine wave starting at a different place. So you can have the displacement be described by A sine omega t, but then the velocity would change to a cosine function. So we say the velocity is phase shifted plus a quarter period with respect to the displacement. So if you can imagine that this cosine is going on back here beyond zero, and then you move the whole wave along, right? It would look like this, right? And I think I went through what the cosine and sine are just the side lengths of a right triangle with a hypotenuse length of 1, right? So the acceleration versus time is found using Newton's second law, A equals F over m, and Hooke's law, F equals minus kx. But now we substitute minus kx for F and the amplitude for x, and we obtain the maximum acceleration is going to be minus Ka, because that's substituting for the F for Newton's second law. And we substitute F with a minus Kx, but X is A, right? So the maximum acceleration is a minus Ka over m. I think we might have gone through this, but it's okay to repeat it. All right, so now let's have a look. The acceleration, of course, is centripetal acceleration, right? And there it is, A max. The component of the acceleration is directed along the same direction as the velocity. But notice how it's a cosine function rather than the sine function that the displacement was. And if we change the A max to minus Ka over m, which we got up above, we get A max, the acceleration at any point in time is minus Ka over m cosine theta. So that would be the same as if we move this, instead of moving this plus, we could move it minus a quarter period. And now you see that this part here lines up with 0, so it's going negative, right? And it makes sense if you think about what's happening with that cart moving backwards and forwards. the acceleration is going to be a maximum when the velocity is a minimum, right? Because that's when the most potential energy is stored. And of course, we can substitute for omega to be 2 pi f again. And so we get that. A is minus Ka over m cosine omega t. Now let's have a look at this little animation where we've got the displacement, the velocity, and the acceleration all starting, okay? See how the acceleration is a maximum when the velocity is a minimum. Want me to do that again? You want to see that again? No? Yes? It will help you remember the relationship. You can see that it's just a phase shift. Yes, it's a sine or a cosine, but all you're doing really when you say sine or cosine is a function which is phase shifted with respect to another, right? So let's summarize. The displacement, x, is equal to a cosine omega t, where a is the amplitude and omega is the angular velocity. Angular velocity is also 2 pi times the frequency. Velocity is the negative of the amplitude times the square root of Ka over m times sine omega t. And the acceleration is minus Ka over m cosine omega t. So let's look at an example. A 0.5 kilogram mass vibrates according to the equation 0.45 cosine 8.40 t, where x is in meters and t is in seconds. Determine the amplitude, the frequency, the total energy, and kinetic energy and potential energy when x equals 0.3 meters. Okay, so let's decode. The mass is 0.5. We don't know what the amplitude is. We don't know the frequency. We don't know the total mechanical energy. We know the displacement we're looking for when we want the kinetic energy and the potential energy. We want the spring constant. We don't know it. Okay. So the equation for displacement in SHM has the form x equals a cosine omega t. It follows that if the mass behaves according to x equals a 0.45 cosine 8.40 t, that a is just 0.5 meters. Do you see that? What we're doing is we're comparing this a here with this number out here, because a is a maximum displacement, right? Amplitude is maximum displacement. And then we look in here and we say omega t, oh, that must be omega, right? Radians per second. You multiply radians per second times the time and you get radians. Yeah. So we can fill those in. Omega is 2 pi f. So the frequency is omega over 2 pi, or 8.4 over 2 pi, or 1.34 hertz. The total mechanical energy is 1/2 Ka squared. Why? Because that's where the maximum potential energy is, where everything is potential energy. So we can say the total mechanical energy at the maximum displacement, which follows Hooke's law, is going to be 1/2 Ka squared. We know what A is, but we need K. How do we find that? Well, we find that from this equation. F equals 1 over 2 pi root K over M. So K is M times 2 pi F squared. But 2 pi F is omega. So it's M times omega squared. That's what K is going to be. So K is 35.28 Newton per meter. You can look at those units and convince yourself that that is in fact correct, right? Total mechanical energy, 1/2 Ka squared. We've now got K, we've got A. We multiply those through to get 3.572 joules. So the potential energy at any point in time is 1/2 Kx squared. We can now substitute for K and the X that we're given. So that means the potential energy at 0.3 meters is 1.5876 joules. And to get the kinetic energy, we just subtract from the total mechanical energy. 1.984 joules. Isn't it nice that I did one of your problems for you? Okay, now we're going to move on. We're going to talk about pendulums, or pendula, I guess. Who's a Latin scholar? Anyone? I'm pretty sure the plural of pendulum is pendula. So a simple pendulum, right? Remember we were talking about a simple harmonic oscillator or simple harmonic motion before. Now we're going to talk about a simple pendulum. It consists of a mass at the end of a lightweight cord. We assume that the cord does not stretch and that its mass is negligible. So here we've got the length L. This is also the length L. This is a displacement X in an arc. This is L sine theta. There's the force of tension. There's the, if you like, the Y component of the weight force, mg cosine theta. And here's the X component of the weight force, mg sine theta. And there's the weight force. Let's have a look. Here's the velocity. It looks a little bit like simple harmonic motion, but it's not. Here's the acceleration, radial acceleration, the tangential acceleration. Notice how the radial acceleration, oh, and here's the forces. There's the tension, there's the weight force. Tension is a maximum down the bottom. I think I should have been sharing my screen, unfortunately. So I'm going to share it now. So I'm sorry to those of you who've been watching. Hopefully you were able to follow along with the presentation. But now I'm at the point where we're looking at the energy in the pendulum. If you go to my presentation, you can actually just step through this yourself and follow along with me. I haven't done anything except what's viewable on the presentation at this point. Okay. The problem with a pendulum is that simple harmonic motion requires that the restoring force be proportional to the negative of the displacement, right? Here we have the force being negative mg sine theta, right? That's what the restoring force is, negative mg sine theta, the component of the weight force. That is not a proportional relationship. Minus mg would be, but minus mg sine theta is not, right? F is proportional to sine theta and not to theta itself in this equation. If it was proportional to theta, we would in fact have simple harmonic motion. So what I would like all of you to do now is to get out your calculators and a piece of paper and a pen. And I'm going to ask you to make a table that has 4 columns. The 4 columns are going to be angle in degrees. And you're going to do from 1 to 10. So you might want to write theta degrees at the top of your column. And then the next column is going to be sine of theta degrees. Okay. And the next thing you're going to do is you're going to find how many radians is that many degrees, right? And I want you to write it out to 4 decimal places. So you're going to write theta radians in the next column. You actually only need 3 columns, sorry. Now write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 down. And now I want you to get the sine of each of those angles in degrees. Make sure your calculator is in degree mode, not radian mode. Hopefully anyone who's watching this is going to be doing the same thing. I think it's important that you do this. You're finding this, the sine of 1 degree, sine of 2 degrees, sine of 3 degrees. And then you're going to go back and you're going to convert degrees to radians. Do it to 4 decimal places, please. 3 columns, theta degrees, 1 through 10. Then the sine of theta degrees. And then you're going to convert theta degrees into theta radians. Now you're going to convert to radians, right? There's 2 pi radians in 360 degrees. So if you want radians, you're going to multiply whatever number you've got there by 2 pi over 360 or pi over 180. So 1 degree is going to be in radians, 1 times pi divided by 180. Two degrees is going to be 2 times pi divided by 180. And remember, you're writing these down to 4 decimal places. How are we doing? Nearly done? You done, Hannah?
I think so.
Okay. Could you make up another column, which is the difference between the sine of the angle and the angle in radians? Just start at the bottom. Start with 10 degrees.
Okay.
The difference between the sine of the angle and the angle in radians. And then divide that by the sine of the angle and multiply by 100 to get the percent difference. Just do that with 10 degrees. Are you done there, Griff?
Yeah.
Yeah. Is there anyone not done the first 3 columns? That is 1 degree through 10, the sine of the angle 1 degree through 10, and then the radians for 1 degree through 10. Are you finished that, Ishan?
Yeah.
Okay, so let's just discuss that for a second. What did you find? Who wants to explain what they found? Okay, Hannah.
They were very close. It seems like the higher the number got, the further apart they got.
Yeah, and what percentage difference did you get per 10 degrees?
I don't know. Wait, how do I find the percent?
So you take the difference and then divide by sine of 10 degrees,
Okay.
and then multiply by 100.
So I got 0.5184.
When after multiplying by 100. So that's 0.5%,
Yeah.
right? 0.5% difference. Not a lot, right? It's not a lot. But 10 degrees, if you saw a pendulum swinging at 10 degrees, you'd say, gee, that's a lot. Especially if it was a big one. So what we can do, and we often do this sort of thing in physics, we realize that, oh, we can make an approximation. This is called the small angle approximation. So long as the angle is less than about 10 degrees for the pendulum that we're considering, we can use the small angle approximation. So now instead of writing sine theta, we just write theta, and magically, the force becomes a proportional relationship because it's now proportional to mg, negative mg theta. Here's the numbers, right? Even at 30 degrees, the error is not too bad, right? So sine of theta is approximately equal to theta in radians when the angle is small. So if that's the case, theta is x over L. L is the chord length, and it's the radius of the arc described by x. Do you see that? So the force is approximately equal to negative mg over big L times x. Yeah? Okay, let's move on. I bring that over. Again, we've got that same equation. So this allows us to infer, you know what I'm saying by infer? If this is a simple harmonic oscillator and we compare it to a Hooke's law based thing, we can see that mg divided by L could be very similar to K, right? Do you see that? So now what we do is we do this sort of clever thing and we substitute for K into the equations for frequency or period that we discussed earlier. And a magical thing happens. There it is substituted for K, right? What happens here? It's G over L. And what's the conclusion then about the behavior of a pendulum and its frequency? What's it dependent on? Or rather, what is it independent of? It's dependent upon the length, yeah. What's it independent of? Sorry? The mass. Yes. It doesn't matter what mass you have on the end of that pendulum. Sort of surprising, right? You would think that the thing would maybe go slower because of inertia, right? But it doesn't. And in fact, the only way that you can get a pendulum to change frequency is either to change the length of the pendulum, L, or to take it to a place where the gravitational force field is different, like the moon, right? So, in summary, as long as the core can be considered massless and the amplitude is small, the period of a pendulum does not depend on the mass. Yes.
Does the length include how big, like the weight of the bottom of the pendulum is, or is it just the cord?
It doesn't, so long as the cord is massless, it doesn't matter what the mass of the bob is.
Yeah. Oh no, I was just wondering, like, if you had two cords that are the same length, then.
Oh, I say you're saying the size of the bob is different. Yeah, I mean, obviously there's an approximation there, right? Because we're assuming it's a point mass, right? But if we went from the center of mass, it would be true.
Okay.
So here's an example. The length of a simple pendulum is 0.66 meters. The pendulum bob has a mass of 310 grams, and it's released at an angle of 12 degrees to the vertical. With what frequency does it vibrate? Assume simple harmonic motion. What is the pendulum bob's speed when it passes through the lowest point of the swing? And what is the total energy stored in this oscillation, assuming no losses? Yeah, you can watch this bit later if you want. Okay, let's decode. Got a length of 0.66 meters, a mass of 0.31 kilos, an angle of 12 degrees. We want to know the frequency. Oh, well, I'm already showing what the maximum velocity is. That's a problem with my animation. and I want to know the total mechanical energy. So here's our pendulum bob. That's the height that the pendulum bob is above its lowest point, h. That is the length of the pendulum bob, of the pendulum cord, minus h. Notice how we've got a nice right triangle there? Okay, so frequency is 1/2 pi root g over L. We can put our numbers in immediately and we get 0.613 hertz. In this particular case, it's actually easier to determine total mechanical energy before the kinetic energy. T, the total mechanical energy U, is equal to mgh, right? H can be determined by calculating that L minus H equals L cosine theta. Do you see that? We rearrange. We have H equals L times 1 minus cosine theta, or 0.0144 meters. That gives us a total mechanical energy of 0.0438 joules. Maximum velocity occurs when all the potential energy is converted to kinetic energy. 1/2 mv squared equals mgh. V max is the square root of 2gh, or 0.531 meters per second. Any questions on that? No? Okay. So now we're going to talk about damped harmonic motion. Damped harmonic motion is harmonic motion with a frictional or drag force. So if you're thinking about an object moving through the air, right, under simple harmonic motion, it could be the drag of the air, depending on what the object's shape is, right? Or it could be the friction of the wheels of this cart. If I set this cart up for you guys to take a look at it again. Just go. That. Like this. Okay, so here's our simple harmonic oscillator. We watch it. If it was a true simple harmonic oscillator, it would keep going forever. But it's not a true simple harmonic oscillator. There is friction on the axles of the wheels. And ultimately, that simple harmonic oscillator slows down to a stop, right? Now, if you think about, if you drew a graph of amplitude versus time, versus time, what would it look like? So what does simple harmonic motion look like normally if it's no drag? It's a, yes?
Oh, would the curves get like
It's sinusoidal, right? That's what it's like for a normal simple harmonic oscillator. But now what we've got is drag. What do you think is going to happen?
It would get closer and it would get shorter.
Whether we get closer?
Uh,
You mean the frequency is going to change?
yeah, like
No, the frequency won't change, but the amplitude changes. Watch this. If you'll carefully watch this, you'll see that the frequency is the same the entire time. That is, the amount of time it takes to go through one cycle stays the same. What happens is the amplitude decreases, right? So let's go back to this. So if the damping is small, we can treat it as an envelope that modifies the undamped oscillation. What do we mean by that? So that's the curve you imagined, I think, the red one, right?
yeah.
Now what you can do, those dotted lines are basically showing you like an exponential decrease, right? It's an envelope. If the frequency was very, very high, right, and those peaks were much closer together, you would see that it would be almost perfect as an envelope, right? Now, there are different types of damping, and we define 3 of them. Underdamping. Underdamping, there are a few small oscillations before the oscillator comes to rest. Now, what I was showing you here is also underdamping, but we're not intending to damp this, right? Then we have critical damping. That's the fastest way to get back to no motion. And then we have overdamping. The system is slowed so much that it takes a long time to get to equilibrium. Now, there are systems where damping is unwanted, such as clocks and watches, mechanical ones, right? And there are systems in which it is wanted. And it often needs to be as close to critical damping as possible, right? These are big shock absorbers. That puts damping on the structure of this building when an earthquake occurs. Aren't they? Those are humongous shock absorbers, right? Like the same thing as a shock absorber on your car. If you didn't have shock absorbers on your car, you hit a pothole and you'd be bouncing all the way to Boston. Here's the shock absorber on a car with the ring spring that you would see if you looked under the car, right? It goes in the center of it. And what it is, it's a piston, not a closely fitting piston, but a loosely fitting piston, which has a viscous fluid in it. So it takes time to push that piston through the viscous fluid. What is a viscous fluid that you can think of? Honey, molasses, right? Those are all viscous. Actually, everything has viscosity. I don't think we finish until 50, right? 43? Okay. So what I'd like you to do is go through, I'm going to show this little video. You don't have to watch it now, but I'm going to leave it running. And I want you guys to watch it. But what I do need to do is share the sound. So I'm going to stop my share. And I'm going to start the share again.
Hey, I'm Grady. Today on Practical Engineering, we're comparing theory to the real world for tuned mass dampers. What do a marble in a bowl, a guitar string, and a skyscraper have in common? Well, you're on the wrong YouTube channel if you think this is a joke. I'm talking about physics. All three are examples of oscillators. An oscillator is just a system that when you displace it from its equilibrium position, it experiences a restoring force. I move this marble from the center of the bowl, it experiences a force, gravity, pulling it back toward the equilibrium position. I pull on the guitar string, the tension in the string increases, trying to pull it back to the center. When the displacing force is released, the system oscillates about the equilibrium point. What about the skyscraper? Maybe this sweet montage will help answer that. Sometimes to the detriment of the hedge fund managers and penthouse denizens on the top floors, a skyscraper can act as an oscillator just like the marble and the guitar string. Wind can induce oscillation in a building just like a tie-down strap on a vehicle. A strong earthquake can also excite the building's resonant frequency just like plucking a guitar string. In most cases, the movement's not enough to threaten the safety of the building itself, but that amount of movement can be profoundly uncomfortable to its occupants. Most of us hold an intrinsic belief that buildings should not move. We don't even think about it. For our entire lives, Wednesdays come after Thursday, the sun has risen in the east, and our domiciles and dwellings have remained static beneath our feet. So you can forgive your subconscious for feeling some amount of terror when such a fundamental belief is shaken, especially when the shaking is literal. It may not be enough to harm the building's structure, but it's certainly enough to cause a 1%er on the top floor to lose his caviar. And buildings aren't good for much if people don't want to be inside them. So engineers have come up with some novel solutions for minimizing this unwelcome vacillation. And I want to talk about one of those today, the tuned mass damper, or TMD. A TMD reduces the amplitude of vibration by absorbing kinetic energy from the system, in this case the swaying motion of a tall building. For a long time, TMDs were relegated to areas with the rest of the building's mechanical equipment, hidden from public view. That changed in 2004 when the Taipei 101 tower finished construction in Taiwan. Rather than hide the world's largest spherical tuned mass damper, the building's designers chose to open it to the public. Taipei 101's TMD has become a draw for tourists and even has its own mascot, the Damper Baby, which looks like it came straight off the island of misfit mascots. Anyway, the publicity associated with the Taipei 101 has sort of unveiled this really cool bit of engineering that is the tuned mass damper, and you can find tons of videos of it in action online. So how does it work? I've constructed this model of a pendulum-style tuned mass damper in a skyscraper. I can pull the cart back and give the building a bump, which excites its resonant frequency just like an earthquake or a strong wind event. The benefit here is that I can do it in a somewhat repeatable fashion so we can evaluate the effectiveness of the damper. For the TMD, the damping comes from the tension of the screw, which is acting as the hinge. I can tighten the screw to increase the damping. The tuning comes from moving this mass up or down on the pendulum shaft. This changes the frequency of the pendulum just like a metronome, which can be tuned to the resonant frequency of the building. I have an accelerometer on top of the building so we can measure its movements, and this is hooked to an Arduino which is sending the data to my laptop. There's more in the description below if you're curious about the data collection. If I lock the pendulum and set the building swaying, we can get a sense of how it would perform with only the building's own natural damping. Plotting the acceleration response, we can see that the model experienced a maximum amplitude of about 4 meters per square second, or half a g, with a period of 0.6 seconds. Frequency is the inverse of period, so we can get the building's fundamental frequency, 1.7 Hz. We can also see that the building has some natural damping just due to the internal friction in its movement. Otherwise, it would just sway indefinitely. We can estimate the model's natural damping ratio using the logarithmic decrement. I get a damping ratio of 0.01. The damping ratio, denoted by one of the tougher Greek letters to draw, zeta, is a measure of how quickly the amplitude decays in an oscillating system. Systems with a damping ratio greater than 1 are said to be overdamped because the system returns to equilibrium without oscillating. Systems with a damping ratio less than 1 are said to be underdamped since they experience some oscillation. If the damping ratio is exactly 1, the system is critically damped and returns to equilibrium as quickly as possible. And if the system is undamped, the oscillation continues indefinitely. There are lesser known damping situations, but we won't get into them in this video. Now that we know an approximate natural frequency of the building, we can introduce the pendulum damper. You may remember from your physics classes that a pendulum's frequency depends on its length. For a frequency of around 1.7 Hz, my pendulum needs to be approximately 3.5 inches long. Now let's try the exact same experiment with the pendulum able to swing freely. The kinetic energy of the building does get transferred to the pendulum at first, but because there's no damping, the pendulum transfers the energy right back into the building. So instead of reducing the amplitude, instead the pendulum just continuously swaps the kinetic energy with the building like a hot potato. You can only imagine that this erratic behavior would be even more alarming to our topmost tenants than the steady but slowly decaying motion of the previous example. Now let's tighten the screw to add some damping to the pendulum and see what happens. Even without looking at the data, you can see a remarkable difference in performance. Looking at the plot of acceleration response, we can see that the peak acceleration was about 3.5 meters per square second, so a reduction of only about 12%. But the big difference is how quickly the motion decays. At the beginning, when the pendulum is swinging, I calculated a damping ratio of over 0.6. That's about 6 times more damping than without the TMD. Once the pendulum stops swinging, the rest of the swaying follows the approximate natural damping ratio of the building itself, as expected. But the majority of the kinetic energy has already been dissipated by the damper, so the amplitude is much lower. Here's a slow speed side by side so you can really compare the two. As silly as this little experiment looks, it's actually not that far off from what engineers do in the real world, usually without the googly eyes. The design phase for just about every major building includes some physical scale model tests. Of course, a tuned mass damper doesn't completely eliminate movement, but we saw that it can certainly make a difference. In engineering, you have inexpensive, you have effective, and you have innovative, and usually you get to pick one, sometimes two. For solving the problem of oscillation in tall buildings though, the tuned mass damper is truly all three. A great example of elegance in engineering.
Okay. Thank you. Welcome.
In many of the world's tall...
So, the next topic is force, vibrations, and resonance. Force vibrations occur when there is a periodic driving force. This force may or may not have the same period as the natural frequency of the system. If the frequency is the same as the natural frequency, the amplitude becomes quite large. This is called resonance. The sharpness of the resonant peak depends on the damping. If the damping is small, it can be quite sharp. If the damping is larger, it is less sharp. Like damping, resonance can be wanted or unwanted. Musical instruments and TV radio receivers depend on it. A very famous case of resonance was what happened to the original Tacoma Narrows Bridge. Now, this is a video of the same setup I've been showing you live. And what I do is I have this device down here, which is pulling periodically on a string, which is connected to one of the springs. So that's putting a periodic driving force into this system. And I use this power supply to change the frequency of that driving force. Now, I'm going to have to show it to you live so that you can see what goes on. Let's connect this up. And what I'm going to do is set that going. And you can see the oscillator there. I'll just move that just a little bit. See, it's sort of a weird motion that's going on there. See, sometimes it increases, sometimes it decreases, but it is a very strange looking motion. Now I can go up with that voltage. Notice now that it's changing its motion a little bit more rapidly. If I go way up, now typically what happens is all right, notice how it's speeding up and slowing down. The reason for that is that we are above the natural frequency. If I go down and near the natural frequency now the thing is going to go off the tracks, right? We've got resonance. We've got resonance occurring. I turn it off before we end up breaking the thing. Even this is not properly aligned. Let's see if we can do it again. So you can see when it's going very fast, it's not resonating. That is, it's not trying to bang itself off the track. If I go down, now I'm near the resonant frequency and it's doing it, but not quite. Now it's hitting the end. I'm going to turn it off at this point. But you get the idea. If we have a particular frequency, the natural, and we have this thing pulling at the same frequency that this thing naturally oscillates, we get a change. If I put a different mass on, I get a different resonant frequency. Now I need to go down. Okay, so notice now that's much more dramatic, I guess. Turn that one off. So the lower the resonant frequency, the slower that driving force at the end. Here's a little video of them breaking a glass with sound at MIT. Here's a big speaker right here. Here's a glass. And they're going to use a strobe light to allow us to see it breaking. But notice how it flexes. Now you can hear the resonant frequency of the glass. So he chooses that. Now look at that actual mode. Pretty dramatic. Okay, and I'm going to stop there. And we will continue this presentation at another time.